8 congruent equilateral triangles, each of a different color, are used to construct a regular octahedron. How many distinguishable ways are there to construct the octahedron? 2 colored octahedrons are distinguishable if neither can be rotated to look just like the other. Okay, so we're going to need to first figure out what is going on, what is being asked. So you've got this octahedron right here, and they are coloring each side a different color. There's 8 sides, right? 1, 2, 3, 4, 5, 6, 7, 8. And each of those sides is an equilateral triangle. And they're basically asking, when you color each side a different color, how many ways of doing that? So one approach to doing this question is by putting a cube inside that octahedron as shown in that diagram. And the vertices of the cube right here, 1, 2, 3, 4, 5, 6, 7, 8, all those vertices will basically be touching each of the 8 faces of the octahedron. And you can see that. And therefore, what we really just need to do is figure out how many combinations are there. So let's go through this. First and foremost, you have 8 colors. All right? Let's pick one vertice, so I'll pick this one right here. And I'll call that 1. And that one is fixed. So vertex 1 is fixed. And for vertex 1, choose any color of the 8. And then now we have to choose colors for the remaining 7 vertices. 1, 2, 3, 4, 5, 6, and then one that we can't see right now. It's behind. So how do you do that? Well, using probability, combinatorics, whatever. There are 7 times 6 times 5 times 4 times 3 times 2 times 1 possible combinations of the remaining 7 colors. And that equals 5,040. But is this the answer? Well, none of the answers are 5,040. And the reason is because this triple counts the total number. And I'll explain why a triple counts. If you have a vertice right here, like that, and this is fixed, the vertices that are joined to it are this one, and this one, correct? So let's label them. Let's say this is 2, and this is 3, and this is 4. Those 3 vertices can be rotated, and once they are rotated, they result in the exact same orientation or situation. So basically we've triple counted because the 3 vertices are joined by the edges of the first vertex, right? Right there, you joined all 3. And when you rotate them, you get 3 rotations for each of these situations. For example, so if you rotate the first one, which is 1, 2, 3, 4, just like that, it can become 1, 4, 2, 3, or 1, 3, 4, 2, like that. So each of these basically has 3 orientations that make it exactly the same. And they used a specific word here, distinguishable. And that means that octahedrons are distinguishable if neither can be rotated to look just like the other. So for these 5,040, we've triple counted because there's 3 that will always be non-distinguishable, right? They'll be the same if you can rotate them. So therefore, since we've triple counted and we've explained why, this number has to be divided by 3. So 5040 has to be divided by 3 to get the distinguishable octahedrons, and that is 1680. So therefore the answer to number 25 is E. So the answer to number 24 is D. Consider sequences of positive real numbers of the form x 2000 y ... in which every term after the first is one less than the product of its two immediate neighbors. For how many different values of x does the term 2001 appear somewhere in the sequence? Okay, so we've got x, 2000, y, and then we keep going like that. And they're saying that there's a fundamental property that every term after the first is equal to one less than the product of its immediate two neighbors. So that means if we take 2000, 2000 is equal to one less than the product of its two neighbors, like this. Okay? So I hope you understand that. Every term after the first is one less than the product of its two immediate neighbors. Okay? So, let's go with that. This is term 1, this is term 2, this is term 3, and we'll try to find a bunch of terms here. Hopefully we'll see a pattern, and that's usually the type of scenario in these kinds of questions. I'll try until T7 and then I'll run out of patience. All right, so for the first one, I've got bring the 1 over. 2001 is equal to xy, and therefore y is equal to 2001 over x. Okay, so let's try to make this neat. Let's not make it messy. Let's use different colors. X is fixed as x, all right? 2000 is fixed as 2000, but y is 2001 over x. All right? Okay. So far, so good. So that was T3 that we just found. Okay. Now let's figure out T4. How do we figure out T4? Well, according to our formula, every time you have a term like T3, it's equal to one less than the product of its two neighbors. So its two neighbors are T2 and T4, like that. Okay? So that means T3, which we already figured out is 2001 over x, is equal to T2, which is 2000, times T4, minus 1. So do a little bit of algebra here, and you're going to get 2001 over x plus 1 is equal to 2000 T4, like that. So this looks like 2001, common denominator is x, like that, and 2000 T4. So T4 is 2001 plus x over 2000x. Okay? So where do I squeeze that in there? Maybe I'll need a little bit more space. So I've got 2001 plus x over 2000x for T4. So the next one we are going to figure out is T5. So we were going to have to go T4 is equal to T3 times T5 minus 1, like that. T4 is 2001 plus x over 2000x is equal to T3, which is 2001 over x, T5 minus 1. So you're going to have 2001 plus x. If you add the 1 to that side and get a common denominator, it'll be 2000x all over 2000x, like that. And this equals 2001 over x T5. So this looks like 2001 plus 2001x over 2000x times x over 2001 is equal to T5. All right. And let's see, does this simplify in any way? If you factor the 2001, you get 1 plus x, and x over 2000x and 2001. Okay, great. The 2000s go and the x's go. So T5 is left with just 1 plus x over 2000. All right. So 1 plus x over 2000. Moving right along. Now we get to, what are we up to now? We have to find T6 next, right? So T6 we will have to use T5 is equal to T4 times T6 minus 1. T5 is 1 plus x over 2000. T4 is equal to 2001 plus x over 2000x. And T6 minus 1, like that. So bring the 1 over and get a common denominator, which will be 2000, like that. And then this is 2001 plus x over, this is a 2000, 2000x, T6. So we've got 2001 plus x over 2000 times cross multiply 2000x over 2001 plus x is equal to T6. And looks like that, oh, this is great. This actually simplifies to just x. All right, great. So I am going to get a pattern. One more, T7. I know this is torture, but it's okay. So one more, and we got, let's see, we're trying to find T7, right? So T6 is equal to T5 times T7 minus 1. X, T5 was, what was T5? 1 plus x over 2000. T7 minus 1. So you got x plus 1 is equal to 1 plus x over 2000, T7, and therefore T7 cross multiply 2001 plus x, so T7 is equal to just 2000. Perfect. So we indeed have a pattern, okay? It's going to repeat. X 2000, 2000 over x, 2001 plus x over 2000 x, 1 plus x over 2000, and then it'll be x 2000, and it'll just keep on going like that. Now, what are they asking in the question? For how many different values of x does the term 2001 appear somewhere in the sequence? What is the value of x if we set these terms equal to 2001? All right. We can figure that out. So the first one, if we set it equal to 2001, we're done. So that pretty much takes care of the first one. How about if we let the second one, 2001 over x equal to 2001? Well, that would mean that x is equal to 1. So this is one value, this is another value. How many different values of x does the term 2001 appear somewhere in the sequence? All right. So if we let x equal to 2001, the term 2001 will appear in the sequence. It will be T1. If we let x equal to 1, this T3 becomes 2001, and therefore the term 2001 will appear in the sequence. All right. So I hope you understand. So again, T4, we got to let that equal to 2001. Probably have a little bit more algebra here. So we got 2001 plus x is equal to 2001 times 2000 x, like that. 2001 is equal to 2001 times 2000 x minus x. Factor out the x and you'll get 2001 times 2000 minus 1, and therefore x is equal to 2001 over 2001 times 2000 minus 1. Okay, so this is another value of x for which the term 2001 will appear in the sequence. So that's a third value. And we've done T1. T2 is fixed, so we can't do T2. We've done T3, we've done T4, and let's see what we get for T5. So T5 is 1 plus x over 2000, and we set that equal to 2001, and therefore 1 plus x is equal to 2001 times 2000, and therefore x is equal to 2001 times 2000 minus 1. So here is a fourth value. So when x is equal to 2001, this expression, T1, will become 2001. When x is equal to 1, T3 will become 2001. When x is equal to this big long number, T4 will become 2001. And when x is equal to 2001 times 2000 minus 1, T5 will become 2001. So we've got 1, 2, 3, 4 values of x that make the terms equal to 2001. And therefore the answer for number 24 is number 25. Let f at x equals x squared plus 6x plus 1. And let R denote the set of the points x, y in the coordinate plane such that fx plus f at y is less than 0, and f at x minus f at y is less than 0. The area of R is closest to. So let's work with these two. We have f at x plus f at y is less than or equal to 0. So f at x is x squared plus 6x plus 1 according to the question, and therefore right here, and therefore f at y would be y squared plus 6y plus 1, and this is all less than or equal to 0. So this looks like, it looks like probably a circle. So x squared plus 6x, if you were to take half of that and square it, if you complete the square, you get 9. And very similarly, y squared plus 6y, if you complete the square, you get 9. And that's 18, but we only have 2, so we have to minus 16. So this becomes x plus 3 squared plus y plus 3 squared is less than or equal to 16. Okay? So that is a circle. This is the equation of a circle, basically. Now let's deal with this guy right here. So we have f at x minus f at y is less than or equal to 0. So that means x squared plus 6x plus 1 minus y squared minus 6y minus 1 is less than or equal to 0. And let's see, this becomes x squared minus y squared plus 6x minus 6y, because the 1's cancel, is less than 0. And I believe the factoring will help us, x minus y, x plus y. Factor out a 6, and this gives x minus y like that. Factor the x minus y, and you'll get x plus y plus 6, like that. And I think that is about as far as we can go there. So now we have to plot these on a graph. So let's make a graph. So we've got like that, x and y. And the first one is basically a circle, and it has a center of -3, -3, and it has a radius of 4. So we'll draw that in this graph. So here is the approximate look of this circle. It has a center at -3, -3, and a radius of 4, approximately like that. And now we have to concentrate on this right here. X minus y times x plus y plus 6 is less than or equal to 0. So this is true in two possible ways. The first way is if x minus y is less than or equal to 0, and the other guy is greater, like that. Okay, so that means that x is less than or equal to y, and x plus y plus 6 greater than 0. We can isolate for one variable here. Let's isolate for y. Y is greater than minus x minus 6. Okay, so these are obviously lines, so we have to plot them. The first one is the line x equals y, right? X equals y is just basically a line that goes, like that. That's the first one, x equals y. Okay? The next one is a line y is equal to minus x minus 6. So y equals minus x minus 6. So I'll plot that one. So when I plot this line here, this guy, it's going to be something like this, approximately. Something like that. So now we have to figure out what are the regions in this diagram that we are interested in. Because if you read the question, R denotes the set of points in the coordinate for which these are all true. So the area of R is closest to. So we have to figure out what is that region. The first equation led us to this, which is the circle. So that whole region right there, inside that, because it's not equal to, it's not just equal to, it's less than. So all the points inside that circle, okay, are part of R, the range, or the basically the set of points that we are trying to identify. So that takes care of the first one. Now the second one, which is right here, gave us another set of points. It gave us case 1, and then it gave us case 2, which is as follows. Case 2 is if x minus y is greater than or equal to 0, and x plus y plus 6 is less than or equal to 0. So that means x is greater than y, and y is less than or equal to minus x minus 6. Okay? So the first scenario, this guy right here, if you were to combine these two, where on the graph would that be? Case 1. X is less than y, and y is greater than minus x minus 6. And I'll label that line y is equal to minus x minus 6. That is this region right here. This region right here. In that region, x is less than or equal to y, and y is greater than or equal to minus x minus 6. Now case 2, x is greater than or equal to y, and y is less than minus x minus 6. Where is it on this diagram? It's this region right here, that region. So the area of those regions that I just shaded in orange is what we have to figure out. So how do we do that? I hope you notice one thing here. Y is equal to x. What is the slope of this line? Well, it's like 1x, right? And the lines are always written in the form y is equal to mx plus b, where m is the slope. So the slope of this line right here is 1, because m in this case is 1. What about this line here? What is the slope? It's like y is equal to minus 1 x minus 6, correct? So the slope of this line is negative 1. So that means you have two lines. One has a slope of 1, the other has a slope of negative 1. Therefore, those two lines are perpendicular. And if they are perpendicular, it means that this is a right angle. Okay? So that allows us to figure out the area of those shaded regions. How? Area of a circle, pi r squared, you know that. If that is a right angle, that's 90 degrees. So it's basically a quarter of the circle, because the full all the way around is 360. 90 degrees divided by 360 is a quarter. And we've got two of those, right? We've got two of those regions. And this diagram, sorry, it's not drawn perfectly to scale, but you get it by now. So that takes care of the first region. And then the second region, not reason, would be the exact same formula. We have a 90-degree angle over 360, and then pi r squared. So here we go. 90 over 360 is 1/4. Pi r. What is r? What is the radius of the circle? It was 4. So 4 squared, again, 1/4 pi 4 squared. So this gives us 16 pi over 4 plus 16 pi over 4. And that's 4 pi plus 4 pi, which is 8 pi. So 8 pi is the answer. The area of r is closest to, okay, they want an actual number. All right, no problem. 8 pi is what? 8 times 3.14. And that is approximately 25.1. Yeah, 25.1. So 25.1, area of r is closest to 25. So number 25 is 25, and that's choice E. 3 points are chosen randomly and independently on a circle. What is the probability that all 3 pairwise distances between the points are less than the radius of the circle? So first, let's explain what it is that they are referring to in the question. You've got a circle, and you've got the center right there, and you've got these 3 points, and I will call them A, B, and C. They're saying that if you create distances between these points, so A to B, B to C, and A to C, all of these must be less than the radius. So this is the radius right here, like that. They want you to create a scenario where AB is less than R, which represents the radius, AC is less than R, and BC is less than R, like that. So in the end, they want you to figure out the probability of that happening. All 3 are less than R. So we have to do this with, I believe, 3 scenarios. So I'll go through each scenario one by one. So scenario number 1, and that is AB is less than R, and we will describe this case. So you've got a circle, and I've labeled A, and I've put B twice. Now, why have I put B twice? Well, because B can be on either side of A. That is not told in the question as to that it can only be on one side. So this is my radius, and I'll draw the radius going to the other b's as well. And now AB is this distance, and of course it's also that distance. Now we want AB to be less than R. Now R is this guy right here. AB will be exactly equal to R when this angle is 60 degrees. That angle is also 60 degrees. As you can see that, because that makes it an equilateral triangle. AB will be less than R when this angle is less than 60 degrees. So written out, AB is less than R when angle BOA is less than 60 degrees. So that means that from here to here, which is 120 degrees, is basically our range for the criteria to make AB less than R. So 120 over the full, complete 360 degrees is our probability of making AB less than R. So 1/3 takes care of this scenario right there. Now we move on to our second scenario, which is AC has to be less than R and BC has to be less than R. So this time I've drawn two circles because we've got to look at it in two different ways. The first is when we have A here and we've got B here, and C is somewhere in between. So C is, let's say, here. And now we can draw our distances. This is, of course, the radius, like that. And AC is here, and BC is right here. And this is R, and this is R. And in a very similar way, this is going to be 60 degrees in terms of our range. Because if you notice, if C is in the middle like that, AC will definitely be less than R, and BC will definitely be less than R. But if C comes out here, then BC will be much bigger than R. So as you can see, C has to be in that 60 degree confined space. So from this guy, we basically get a scenario of 60 degrees over 360, which is 1/6. 1/6 is basically the probability of this scenario and this criteria. Okay? But there's another way of drawing ACB, and I think that is the most challenging part of the question, and that is as follows. The other way of drawing AC and B together is when A and B are on the exact same point, and C is on either side. It can be on this side or on that side. And when you have that scenario, you basically get the following. You get a line from the center till C and just one line to AB because A and B are on the same point. Now, very similarly to the first scenario up here, this angle has to be 60 degrees and this angle has to be 60 degrees. That is the only way that you can create the absolute boundary for where C can be. Because at this point, if you notice, very similar to before, this is the radius, this is the radius, this is the radius. And if CA is also equal to R and AC or BC is also equal to R, these basically become equilateral triangles. So C can be here, but it most likely will be here or here or here. It's got to be in a way so that the angle is less than 60. Very similar to over here, the angle, I'll write it here, COA has to be less than 60 in order for these conditions to be met. So this scenario gives you an additional probability. It gives you 120 over 360, and that's 1/3. Now, we can have this or we can have this. 1 over 3. And in probability, if you have one or the other, you add them. So 1 over 6 plus 1 over 3. And we have to find the average probability. And how do you find the average probability? Well, just like any other average, you have to divide by 2. We added two numbers, you divide by 2. So this looks like 1 over 6 plus 3 over 6 is 1 over 6 plus 2 over 6, all over 2. So this looks like 3 over 6 over 2. Invert and multiply, and you'll get 3 over 12, which is 1/4. All right? So 1/4 is this scenario right here, scenario number 2, and 1/3 was the probability for scenario number 1. Now we want all these scenarios together. So this and this guy right here. If you have to combine with the and in a probability question, you multiply the probabilities. So we have to multiply 1/3 and 1/4 to get the final overall probability, and that gives you 1 over 12. So this is the answer to the question, and that would mean number 25 is D. Given that 2 to the power of 2004 is a 604-digit number whose first digit is 1, how many elements of the set 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, ... all the way to 2 to the power of 2003 have a first digit of 4? So what I'm going to do is I'm going to make a list and see if there's any kind of a pattern. So I've got 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. And for each, I will write the first digit. So here is the list here. I've written out till 2 to the power of 19. And you'll see a little bit of a pattern here. 1, 2, 4, 8, and then 1, 3, 6, and then 1, 2, 5, and then 1, 2, 4, 8, 1, 3, 6, and then 1, 2, 5. And you think, oh, okay, no problem. I got this all figured out. And that's what I thought too. But then I said, well, it's number 25 on AMC 12. So the hardest, well, not necessarily the hardest question, but definitely one of the hardest questions on the senior level math contest. It cannot possibly be this straightforward. And it isn't. Why? Why isn't it this straightforward? What's the story here? And I'll tell you, because it looks like it follows this pattern, right? And it does for the first 2 to the power of 19. But eventually what happens is something very unfortunate. And that is that this guy, 1, 2, 4, 8, it changes. It becomes 1, 2, 4, 9. And that happens because one of the numbers becomes so large, it becomes whatever, like 4, I don't even remember, but 4.5 million or something like that. And then when you double it, it becomes a number that starts with the digit 9. And that is the problem. That is the thing that makes this question so challenging. The good news is that the pattern does continue, but you've got this little change here. To make matters worse, this pattern also changes eventually. Initially it's 1, 3, 6, 1, 3, 6, right? But eventually it becomes 1, 3, 7. For the same reason, that eventually the numbers become big, and then when you double it, it becomes 7 as the first digit. All right, well, how do you approach this then? Okay, try to explain this as carefully as I can. So look at first those 4. You got 4 of them, right? There's 4 numbers in a pattern. The next one is 3 numbers in a pattern. The next one is 3, and then 4, and then 3, and then 3 like that. Okay? So that's pretty straightforward right there. So before I start explaining this whole big subset here, let me just explain it for this subset until 2 to the power of 19. Okay? And then I'll extrapolate till 2 to the power of 2003. Okay, so let's just look at these guys. So let's move this question up. Let's concentrate on what we have on the screen. Okay. We've got 2 to the power of 0 until 2 to the power of 19. Correct? So we've got how many terms? We've got 20 terms. All right. Now, how many little subsets do I have? I got one here, one here, one here, one here, here, and here. I've got 6 of them, right? Okay, great. 6 of those little subsets. But I'm going to break them up into subsets of 4 and subsets of 3. Okay? So how many subsets of 4 do I have? I've got 2 of those guys. This one and this one. And each of them has 4 numbers in it. Okay? Then how many subsets of 3? Well, I've got these 4 groups. So I've got 4 of them. And each of them has how many numbers? Has 3. And if you total it all up, it should equal 20. And it does. 2 times 4 is 8. 8 plus 12 is 20. Okay? So 20 tells me how many terms or how many powers of 2. And we indeed have 20 of them, right? 2000 until 2019. So I hope you understood how this equation was calculated. All right? Now, one more thing is that when you look at these numbers, right? I want you to make a list of the numbers at the end of each subset. So this guy, for example, is 8. Correct? So that number is already there. This, 2 to the power of 6, I want you to write that number out. It's 64. 2 to the power of 9 is 512. Just the ones at the end of the subset, and then I'll explain what I mean. 2 to the power of, let's match this up, it was 2 to the power of 13. And that's 8192. 2 to the power of 16 right here, 65536. And the last one, 2 to the power of 19, 524288. Now, why? What's the point here? Why do I need those? Well, now I want you to count the number of digits in each of those numbers. Well, in 8, there's only 1 digit. So I'll write that here, number of digits. And this will become clear once I finish. Number of digits in 64, well, there's 2. Number of digits in 512, 3. Number of digits in 8192, 4. Number of digits in 536 is 5. And the number of digits in 524288 is 6. Do you see a pattern there? 1, 2, 3, 4, 5, 6. Correct? So in this mathematical formula, if we get to the end there, that final number, in our case, has 6 digits, and that must equal this number plus this number. And it does. So that is the key to this question. It's a tough question. I'm not going to, brush this off and say, oh, you can do this. This is tough. It's not easy. So what I have to do is I have to come up with a formula. And I can do that. Basically, I'm going to let this be x, right? If I'm extrapolating all the way till 2000, or 2 to the power of 2003, right? Yeah. And I'm going to let this one be y. So in a very similar way, it'll be x times 4 plus y times 3. And it's not 20 this time. It's how many? 2004. Why? Because in our set, we have 2 to the power of 0 all the way to 2 to the power of 2003. And that's 2004 numbers. Okay? So I'm following basically this formula up here. I'm just extrapolating it to 2004 because that's how far they want us to go for powers of 2. Okay, and then we also figured out this little neat formula that x plus y is equal to the digits in the very last one. Okay, now do we know that? Well, here we know it's 6, but what's the number of digits in the very last one? They tell you in the question. Well, they tell you some of it. 2 to the power of 2004 is a 604-digit number. Okay? All right. Well, geez, does that help me? I mean, I want to know how many digits are in 2 to the power of 2003. All right. Well, how do I work with that? Well, 2 to the power of 2004 is 1 after 2 to the power of 2003, right? Now they tell you a little bit of information about 2 to the power of 2004. It has 604 digits and the first digit is 1. So we've got 604 digits, right? Number of digits. And first number, first digit. Now we need to figure out the same information for 2003. Well, for 2 to the power of 2003, I don't know. I have no idea what is the first digit. But the good news is that this is a 1. And therefore, because it's a 1, this basically means that it's the start of another subset. You notice the start of any subset is always 1. Did you notice that right there? So 2 to the power of 2003 is 1 before it. So if it's 1 before it, its first digit could be 8, its first digit could be 6, its first digit could be 5, right? So we don't know, so I'm going to put a question mark there. And that's okay, we don't need to know, but we definitely need to know the number of digits. If the number of digits is 604 for 2 to the power of 2004, 2 to the power of 2003 will have how many digits? Well, remember, let's look at this one here. This subset, these guys had 6 digits, right? For their numbers. The next subset before it, the number had 5 digits. So it's 1 less. So this has 603 digits. Okay? So I wanted to take that slow there. 2 to the power of 2003 has 603 digits. All right, let's go back to our formula. X plus y equals the number of digits in the very last term. 2 to the power of 2003, we just figured out, has 603 digits. Okay, so that is our system of equations, this one and this one. If we solve this, we will get values for x and y. Now, okay, well, how does that help us? X represents what? It represents the number of times that 4 will appear as the first digit. Right? Let's go back and take a look at that a little bit. X in our little formula here was 2. Correct? How many times did 4 appear as the first digit? Once here, once here. 2. Everywhere else, there's no 4. You see how that works? So x represents the number of times that 4 will appear as the first digit. So note, x represents the number of times that 4 appears as the first digit, and that is what they are asking in the question. So let's use these two equations to solve for x and y. So from this guy here, we basically get that y is equal to 603 minus x. And we can substitute that into here, and we will get 4x plus 3y is equal to 2004. 4x plus 3 times 603 minus x is 2004. So 4x plus 1809 minus 3x is 2004. So this looks like x, and this is 2004 minus 1809, which is equal to 195, like that. So there you have it. And since x represents the number of times that 4 appears as the first digit, 4 appears as the first digit 195 times for the set that goes all the way up to 2 to the power of 2003. And therefore, number 25, the answer is B. Six ants simultaneously stand on the 6 vertices of a regular octahedron, with each ant at a different vertex. Simultaneously and independently, each ant moves from its vertex to one of the 4 adjacent vertices, each with equal probability. What is the probability? That no 2 ants arrive at the same vertex. This is a octahedron, and let's say we have ants represented by the red dots at each of the vertices, and of course we've got 6 of them, and they're saying that these ants are going to start moving. And let's start labeling these vertices. We got A here, B, C, D, E, and finally F at the bottom. Now these ants move. So for example, this ant here will move down to this position. And this ant here perhaps will move down to this position, and so on, right? What they're saying is that you want to be able to create a situation that when they do move and land at some other adjacent vertice, that no 2 ants are at the same vertice. So if they started in the positions of A, B, C, D, E, and F, if they move, they have to all move and land on a different vertice. So for example, they could end up, A could go to, let's say, B, B could go to C, C could go to D, D could go to F, E could go to A, and F could go to what's left over, which I believe is E. See, this is a scenario that works. I hope I did that properly. So what doesn't work is if, 2 ants end up at A. So A moves to D, but then F also moves to D. That's not going to work. That's no good. So they want you to figure out that probability. Well, with any probability question, the very first thing is, of course, to figure out the denominator. That's going to be much simpler. The denominator in this question is going to be the number of possibilities, total number. Well, each ant has 4 possible vertices that can be traveled to, 4 adjacent vertices. So there's 6 ants, right? 1, 2, 3, 4, 5, 6. Each ant has 4 possible choices. 4 times 4 times 4 times 4 times 4, which is 4 to the power of 6. That is the denominator. Now the numerator, of course, is what we have to figure out, and that's a little bit more challenging. So here we go. So to break this problem up into something that makes it easy to understand, I'm going to first start with the ant that's at A. And let's say the ant at A travels to B. Correct? Now, the ant at A has how many possible choices? 4, like any ant. They can only go to an adjacent vertice. So if you're originally here, you can only go to B, C, D, or E. Can't go to F because that is not an adjacent vertice. So when A travels to B, that is only one of 4 options. All right? So whatever scenario I get for this, at the very end, I will have to multiply it by 4, correct? Because B is only one of the 4 options. The same scenario will hold true for going to C, for going to E, and for going to D. So if you can figure out for 1, you can just multiply at the end by 4. Okay, so that's where I'm starting. And when I start with A going to B, it's going to create 3 cases for me. Case 1, case 2, and case 3. Case 1 and case 2 and case 3 for what? We've already decided that A is going to go to B. Case 1, 2, and 3 for F, for this guy. Concentrate on him now, because he's on a vertice that is not adjacent. So case 1, we're going to put F going to C. Okay? He's going to travel from here to here. And A is traveling from here to there. All right? That is my scenario. So here we go with case number 1. Now, how many ants did we have? We had A, B, C, D, E, and F. These are the ants. These are where they are originally. Now, we have decided in our question that A is going to B, correct? So A is going to B, like that. So we don't need to worry about A, and we don't need to worry about going to B. Now, F, we also decided, is going to C. So F is going to C. Now, we need to figure out, where does everybody else go? Bring the diagram back so it helps you visually. B, the ant that's at B, what possibilities does he or she have? He can go to either A, E, or F. Okay? A, E, or F are the choices for B. What about C? The ant that's here, where can that ant go? Well, only the adjacent vertices. C can go to either A, D, or F. What about the ant at D? What are the choices there? Well, can go to A, E, or F. A, E, or F. What about C? Why can't I go C? Well, because C is already taken. We have placed F there, remember? So just in case you're wondering. And then finally, E in a very similar way. Where can E go? E go A, D, and F. All right? So hopefully that makes sense. So let's keep this. All right, now we have to figure out our scenario. So here we go. B. Let's start with the very first one. Let's go in order, so avoid any confusion. B can go to A. Great. How about C? C, let's go right in order. Can I go to A? No, because B's already gone there. And we don't want any 2 on the same vertice. So let's put C at D. Let's go to the next one. D. Where can D go? Can it go to A? No, no, no. We don't want that scenario. But it can go to E. Then our last guy, E. B, C, D, E. Where can E go? Can he go to A? No. D? No. He has to go to F. All right? So that's one scenario. Let's say how many more. And I'll let you kind of do this. I'll just write them out. Right? Because I don't think you really need to hear me rationalize every single one. So I will write out all the possibilities, and I'll come back and we'll discuss it. So there you have it. There are all the scenarios in a very systematic way. I've written them all out. This is scenario number 1, number 2, number 3, number 4, 5, 6, 7, 8. So we've got 8 possible ways that this can be done, with F going to C and our original A going to B. Okay? So now let's move on to case number 2. A is still going to B, but now case number 2 involves F going to D this time. And in a very similar way, I won't torture you with all the details because by now I think you figured it out. I will just write out the possible ways that we can place all the other ants. And this is the possible scenarios. And this time we only have 4 for the case where F goes to D. And then the parent is always the same, right? The parent is A going to B. And then we have one final scenario for A going to B, and that is where case number 3 comes in. And that is where F is going to E. And the good news is that this is the exact same as case number 1 in terms of the way you would approach it. So without laboring this to death, I'll just write that it's 8 possible scenarios, very similar to the way I did here in case number 1. So there you go, we're done. 8 plus 4 plus 8 is 20. 20 possible ways that you can arrange these ants if A is going to B. Now remember, I told you at the beginning that that's only one of 4 possible options for A. If A goes to B, you've got 20 possibilities like we just figured out. But A can also go to C, D, or E. So if A goes to B, you've got 20, just like how I did. But if A goes to C, we can also figure out 20 ways. If A goes to D, we can also figure out 20 ways. And then finally, if A goes to E, we can also figure out 20 ways. So in total, it's 80. And if you remember, probably by now you've forgotten the denominator. Our numerator we just figured out was 80. The denominator was 4 to the power of 6. So this is the final answer. Now this is equivalent to 80 over 4096, the fraction. If we divide top and bottom by 16, you'll get 5 over 256, and that is in lowest terms. 5 over 256 is choice A for number 25. A sequence A1, A2, ... of non-negative integers is defined by the rule AN plus 1 equals AN plus 1 minus AN, the absolute value of that, for n greater than 1. If A1 equals 999 and A2 is less than 999 and A to the 2006 is equal to 1, how many different values of A2 are possible? So we can use a table format and figure out A1, A2, A3, A4, and so on, and see what this behaves like. And I'll just do it up until A9, A10, and then of course we can extrapolate that all the way down to A to the 2006. Okay? Now we are told that A to the 1 is fixed as 999. Okay? And let's use our relationship here that AN plus 2 is equal to the absolute value of AN plus 1 minus AN. So we've got AN plus 2 is equal to the absolute value of AN plus 1 minus A to the n. All right, so here we go. I have to start somewhere, right, with A2. They're saying that A2 is less than 999. So I'll start with 1. Okay? And if that's the case, and I start using this rule, let's see what happens. 1 minus 999 is negative 998, but I have to take the absolute value, so 998. Then 998 minus 1, 997. 997 minus 998, which is negative 1. Absolute value gives me 1. Continuing this, we get 996, 995, 1. And then continuing in the same format, we'll get 994, 993, and then just keeps on going, dot, dot, dot. But we are told that A2006 is equal to 1. Now, does this match? Well, I noticed that the ones are kind of repeating, right? A2, A5, A8, and so on. So it looks like if my A has 1 less than a multiple of 3, it will be 1. So for example, A5, 5 plus 1 is 6, and 6 is a multiple of 3. A8, 8 plus 1 is 9, and 9 is a multiple of 3. So if 2006 plus 1 is a multiple of 3, this will work. And it is. So this checks out. And in a very similar way, you can make a table. And when they do, I'll leave that to you to make this big long table. When they do make this table, they conclude that A2 must be odd, the value of A2. The other thing they conclude is that A2 can't be a divisor of 999. Okay, well, first of all, from 1 to 199 inclusive, 999 inclusive, I should say, how many odd integers are there? Well, 499 odd integers. And then we have to eliminate from this 499 all the multiples of 999. Well, 999 is equal to 3 to the power of 3 times 37. 9 times 37. 27 times 37. So that means we have to get rid of all the multiples of 3. We also have to get rid of all the multiples of 37. Those are the prime factors. And we also have to take in the fact that when we take away all the multiples of 3 and 37, we will have taken away multiples of 3 times 37 twice. So we have to add those back. So how many multiples of 3 do we have between this 499 odd integers? Well, we got 166 of them. How many multiples of 37? There's 13. And then this double counts multiples of 3 times 37. And there's 4 of those guys. So our grand total for the total possible values of A2 will be 499 minus the 166 minus the 13, and then add back 4 because we subtracted those twice when we subtract 166 and 13, so we've got to add 1 set back. And if you do this, this becomes 324. And that would make this number 25 answer choice B. And just for the sake of completion, I'm including the official solution to this very difficult problem here. So read this, discuss it with your fellow math contest competitors, and I hope that you will be able to get a complete understanding of this number 25. Points A, B, C, D, and E are located in three-dimensional space with AB equal to BC, equal to CD, equal to DE, equal to EA, equal to 2. Angles ABC, CDE, and DEA are equal to 90 degrees. The plane of ABC is parallel to DE. What is the area of triangle BDE? Let's draw this the best that we can, the best that I can, to try to explain it. So I'm just going to use the coordinate plane x, y, z. And I hope this will make sense. There's many ways of doing this question. There's no right way, there's no wrong way, in the sense like, as long as you understand it. So first, without making it too complicated, I'm just going to take it one step at a time. First, I'll just draw AB, this guy right here. And I have no idea, so I'll just put it here. Okay, that's AB. Then I'm going to draw BC. Now, they tell me that ABC is 90 degrees. So that tells me that BC is probably something like this. So before I move any further, let me label that. A, B, that corner right there, and C. And I'll put in that 90 degree. Okay, so far so good. You're with me? Following? All right, next we've drawn what? AB, and we've drawn BC. Now let's draw CD. Where is CD? I have no clue. But they tell me, did they tell me anything? Well, they tell me that CDE is 90 degrees right there. Okay, so CDE. All right, D perhaps is here, and then E perhaps is here. If that is the case, this is D, and this is E, and they tell me that CDE is 90 degrees. So that means this angle here is a right angle. Okay, so far I think I'm okay. Let's keep going here. Next I got to draw, I've drawn so far CDDA. Okay, I only have one left. EA. Well, EA is obviously right here, the connection between these two guys. All right. And they tell me that that angle DEA is also 90 degrees. So DEA is 90. Okay, looking at this, it looks to me as if this is kind of like a box. Perhaps. Like, I don't want to get anything confusing here, but you see how this is sort of like a box? And how this is sort of... Does that make sense? All right, so what do they want me to figure out? The area of BDE. BDE, that triangle. Okay, so B, first of all, I have to join it to D, and then BDE. So this triangle, they want me to figure out that area. Okay, well, that should be relatively simple. Why? Because I believe that this angle between here and here is a right angle, like that. Okay, don't get confused. I drew a line between B and D, and now I'm talking about this angle between this line and this line. Okay, so that means I need to figure out the sizes now. They tell me that AB is 2, BC is 2, CD is 2, DE is 2, and EA is 2. Okay? Now, if this line is directly, above this line, the way I've drawn it, right? That it must also be 2. And if that's the case, then that means that this is an equilateral triangle. So this angle, even though it doesn't seem like it, is 60 degrees. That's got to be 60 degrees. This has got to be 60 degrees. Okay, that's the only way this would match. So we are now down to the final step, which is figuring out the area of BDE. Well, it's just going to be 1/2 base times height. Let's see here, BDE. This is the base, and that's 2. And the height is from there to there, which is also 2. And therefore, this is going to be 2 times 2, 4, divided by 2 is 2. So the answer to number 25 is C. Let ABCD be a trapezoid with AB parallel to CD. AB is equal to 11, BC is equal to 5, and CD is equal to 19, and DA is 7. Bisectors of angle A and angle D meet at P. Bisectors of angle B and angle C meet at Q. What is the area of hexagon ABQCDP? Our trapezoid looks something like this, right? This is A, this is B, C, and D. And then they've given us a lot of information. First of all, AB is 11, BC is 5, CD is 19, and AD is 7. All right? The first thing in this question that I'd like to do is figure out an altitude, or a height, I should say. And that is, of course, from top to bottom like this. And I'll just draw the same thing on the other side, starting from B. And since these are heights, they will meet the bottom at right angles. And this will allow me, hopefully, to calculate the height. So I'll label the height H, and here we go. So this distance from there to there, I don't know, so I'll just call that X. And this distance from there to there, I don't know, so I'll call it Y. Now, very quickly, I noticed one thing is that this is 11. Since they tell you that AB is parallel to CD, this distance is 11. So if that distance is 11, that means that 11 plus X plus Y is equal to 19, right? And that means X plus Y is equal to 8, and therefore Y is equal to 8 minus X. So that's a little bit more beneficial to us since we only have to deal with one variable. All right, now we've got two Pythagorean relationships, there and there, so let's go. The first one, we've got h squared plus x squared is equal to 7 squared, this triangle right here. And the second one, we get h squared plus 8 minus x squared is equal to 5 squared, like that. All right, so that's equation 1 and 2. I'll call this one equation 1. I'll call this equation 2. And then, since we have two equations, two variables, we can solve for x and y. Or x and h, I should say. You can solve for y too if you'd like. So, many ways of doing this. I'm just going to subtract this. I think that should be sufficient. Immediately, you'll get rid of the 8 squares. So, I got x squared. Let's expand that. So that's going to give me minus 64, I'm subtracting, plus 16x minus x squared, and then the other side was 49 minus 25. So this just gives me 16x is equal to 49 minus 25 plus 64. And solving, I get x is equal to 5.5. Or if you want to write it out as 11 over 2. Either way. If you want to solve for y, you can. It'll be 2.5 or 5 over 2. But what we really want is h. H, plug it back into any of these. And you get, let's see here, 49 minus x squared, so 11 over 2 squared, like that, is h squared. So this becomes 49 minus 121 over 4, again a common denominator, 196 minus 121 over 4, and that is going to be 75 over 4 is 8 squared. And therefore h is going to be the root of that, which is 5 root 3 over 2. So that is a very important finding. We just found the height. So that is the first part of this question. The next part of the question involves the same diagram, of course, but we're going to look at it in a slightly different way. Now let me explain what's happening here. This is my top to bottom h that I just figured out, but instead of calling it h, I'm going to call it x and x. Okay? And then the distance from P to AD is also going to be x. Now I'll explain why. And the same story holds true here. Now remember, what was P and Q? If you remember back to the original question, what they did was they took angle bisectors from A and another angle bisector from D and said that the point where they meet is P. That's what P is. Similarly, on the other side, they took an angle bisector of B and an angle bisector of C, and they said that the point that those angle bisectors meet is Q. All right? And our goal at the end of the question is to figure out the area of the shape ABQ CDP. That is our goal. So ABQ CDP. That shape is what we have to figure out. Well, I'm sure you can see that shape can be figured out with the following equation. It would be the full trapezoid ABCD minus those two triangles, right? If you subtract from it this triangle right here, which is BCQ, and this triangle right here, which is ADP. If you do that, you'll be able to get the area of that shape. So that is our goal. Now let's turn back our attention to these x's. How do we know this, first of all? We can label it, but how do we know that is true? Well, it's true because by definition, when you have angle bisectors, they're always equidistant from the sides of the angle. And that is a very important point that I think is challenging. A lot of people may not know that, or if they do know it, may not recognize it in this question. So based on that principle, P will be equidistant from AB, it will be equidistant from a CD, and from AD. And that is why we were able to put x's there, since P is equidistant from those three sides. Okay, and in a very similar way, we'll label the same kind of story over there for Q. All right, great. Now we can use this formula to figure out our question. So we've got ABQ CDP is equal to ABCD minus BCQ minus ADP. Well, ABCD, if you remember the area of the trapezoid, it will be 11 plus 19, right? That side plus that side, divided by 2, times the height. And the height we figured out up here is 5 root 3 over 2. So that's very important. And then BCQ, the good news is we figured out that that is a right triangle, because if something is equidistant and you draw a line from it to the other side, it's the shortest possible distance, which is a straight line that's perpendicular, and that's why that's a right angle. So this was a very important point that we had to recognize to solve this question. So that just becomes 1/2 base times height. The base is 5 and the height is x. Now x is h over 2, right? If you look at that diagram, you'll be able to notice that. So I'll just put h over 2 right there. And then similarly, ADP, which is right here, ADP, that's also 1/2 base times height. The base is 7, and the height is x, which is h over 2. So there we go. This is what we are going to solve. So this gives me 15 times 5 over 2 root 3. This gives me 5 over 4, and h was equal to 5 root 3 over 2. This is going to give me 7 over 4, and h, which is 5 root 3 over 2. Okay, looks like there's 5 root 3's over 2 everywhere, so I can factor them out, make the math easy. And this gives me just 5 minus 5 over 4 minus 7 over 4. 5 root 3 over 2. And this looks like it's make this a fraction. So 60 minus 12 over 4. And that looks like 48 over 4, which is 12. So 5 root 3 over 2 times 12. And that's going to be 6 times 5, which is 30 root 3. And there you go. 30 root 3 is the answer to this question. And that would be, for number 25, choice B. The set G is defined by the points x, y with integer coordinates, and the absolute value of x is between 3 and 7, and the absolute value of y is between 3 and 7. How many squares of a side at least 6 have their 4 vertices in G? For every integer n greater than or equal to 2, let pow n be the largest power of the largest prime that divides n. For example, pow of 144, which is pow of 2 to the 4 times 3 to the 2, is 3 to the 2. What is the largest integer m such that 2010 to the power of m divides the product of pow n from n equals 2 to 5,300? This is a very, very interesting question. It's a very good question, and I'll try my best to explain it. So first and foremost, do you know what this means? Most likely, if you're in grade 12, it just means you're multiplying this guy for every value of n from n2 to 5,300. So it's like a continuous multiplication. And what they're asking in the question is that if you do that, you take this, it's going to look like a pi when I write it, but it's not. It's a different symbol. So if you do this whole thing, and it's obviously a very, very big number, and then you divide by this 2010 to the m, what's the largest possible value you can have for m such that this is an integer? Because this statement, such that 2010 m divides this, means that when you do the division, it turns out to be some integer. So I'll just write I for integer. So how do we approach this? Well, the first thing I want to do is break up this 2010. Instead of writing 2010 to the m, I want to break it up into its prime factors. And the prime factors of 2010 are 2, 3, 5, and 67. And therefore each of them will be to the power of m when you break it up like that. And of course this is a multiplication. Now this might take a little bit of practice. On a math contest you've got 3 minutes. So the challenge of this question, in my opinion, is not the difficulty of the question but the time constraint. If I sent you home for the weekend and said, hey, take this question home, I guarantee you'd be able to do it because you've got, whatever amount of time you need. But you got 3 minutes on a math contest. That's the challenge, because otherwise it's actually a very cool little question. It's not really that difficult. As you can see, they've even given you an example. So what we will do is only concentrate on this one, 67. Now you might say, well, how do you know? How do you know 67 is the one you have to concentrate on? Why aren't you going to concentrate on 2 or 3 or 5? And that's a debate I've read on the internet. It's a great debate. And the answer is because you don't have time. That's the actual answer to that question, because 67 is way larger than these numbers, and I'm pretty much certain that there's going to be a whole lot of 2s and 3s and 5s in this whole big thing, but there's not going to be as many 67s. So if 67 divides this, then I'm pretty sure that is going to be the largest value of m. So here we go. I'm going to just write out 67 in terms of this product. So we've got the pow of 67. If n was 67, then it would become 67, right? Because we're basically going by that definition right there. You take any number, you break it up into its prime factors, and then you extract from it the largest one. So in 67, that's just 1 times 67. The largest prime factor obviously is 67. So power of 67 becomes just 67. Okay? And in a very similar way, you can do that for any multiple of 67. So for example, if you have power of 67 times 2, that, according to this definition, is also going to be 67, since you're taking the largest prime. And very similarly, the same story holds true for any multiple of 67, with a few exceptions. So I'm not going to obviously write them all out, but I'll just write ... and then I'll write the exceptions. So first and foremost, we're going to get all the way down to 67 times 66. All of these will have 67 as its largest prime until we get to power of 67 times 67. This one, when you extract the prime, you're extracting 67 squared. Okay? So that is a little unique. So because it's unique, I'm going to put a little underline like that. And then you just keep going. Powers of 67. The next one is 67 times 68. Like that. And I'll write out all of them until the very end. And that's it. That's to the very end. And you say, well, how do you know it ends there? Well, because 67 times 79 is 5,293. And we're only going up until 5300. If you do 67 times 80, which would be the next one, that's 5,360. And that's greater than where we're going up to. So this is the last one that involves 67. Now let's talk about this. This is where the question gets interesting. For each of these, right, we're only going to get 67. And therefore, when we get 67, we only get 1 as the exponent. Okay? All of these exponents are going to be added up, and that is what they're asking for. This one also gives 1 as the exponent for 67. This is 1, this is 1. This is 2, though. And you see the answer choices are very similar, so they're making that assumption that you're going to miss this guy. Okay, let's keep going. This gives you 1. This gives you 1. This gives you 1. Now, this is the tricky one. Why? Because 71 is a prime. So the power of 67 times 71 will not be 67. It will be 71. So you don't get any exponent for 67. You see that there? And then this one will give you 1 because 72 is not prime. But 73 is a prime. So the power of that will give you 73. This one will give you 1. This one will give you 1. 76 will also give you 1. 1, 1, and this one, 79, is a prime, so this one will give you 79. Now for all of these, I didn't write the 67, right? It's really 67 to the power of 1. I just wrote the exponent. So our task now is to add up all of the exponents. Okay, no problem. From the very first one up until this one, there's 66, correct? I didn't write them all in, but we have 67 times 1, 67 times 2, 67 times 3, all the way till 67 times 66. And each of those give an exponent of 1. So we got 66, these guys right here. Those give 66 in terms of when you add up the exponents of 67 to the power of 1, 66 times. This one here gives you 2. And then we're going to add these manually. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I got 9 there. So 9 plus 2, which is 11, plus 66, which is 77. That is going to be up here, if you did this whole thing, it would be 67 to the power of 77. And therefore, the largest possible m in the denominator is 77. Because if it's anything greater than 77, this will not be an integer. Right? So I hope that makes sense. It's a really good question. Practice it. I hope I have explained it the best I can. If you're still unclear, take it home for the weekend. Spend more than 3 minutes on it. And I hope you come to the same conclusion. So number 25, the answer is D. For every m and k integers with k odd, denote by bracket mk the integer closest to m over k. For every odd integer k, let pk be the probability that n over k bracket plus 100 minus n over k bracket equals 100 over k bracket. For an integer n, randomly chosen from the interval n is between 1 and 99 factorial, what is the minimum possible value of pk over the odd integers k in the interval k between 1 to 99? Well, the first thing I'd like to notice, or help you notice, is that if you take the original equation that they give you, and instead of n, if you make a substitute of n minus k, it still remains valid, right? You can put that in there. So this becomes 100 minus n minus k, like this. And this side is, of course, unchanged as 100 over k. Now, what that helps us, hopefully, is understand that we can just consider p at k for values of n that are less than k, because it will always hold true. So if we just use this interval for n, it will make it a little bit more easier for us, and that's perfectly valid for this question. No need to go all the way up to 99 factorial, way too time consuming. So let's move forward with that. Now, another thing I wanted to point out is in this question, look at the answer choices, right? P at k is what we are interested in, right? The minimum possible value of p at k. Now, the probability of anything is always a fraction, where you have a numerator and you have a denominator. But the denominator is the total number of cases. Now, if n is between 1 and k, the range is from 1 to k, so the total number of cases is k. So the denominator is going to be k. So all we have to do is just look at values of k that match these denominators. And we actually only have to look at those 4 because k is odd. So we don't even need to look at 2 because 2 is even. So that, I think, definitely helps us out even more with regard to this question. So all we have to do is look at values of k, 13, 67, 87, and 99. Now we will start looking at this expression one at a time. This one right up here. We want, first and foremost, 100 over k to equal, let's say, 1. Let's start with that. That will only happen if k is greater than or equal to 67. Try it in a calculator, you'll see. And that means that we don't even need to look at 13 because 13 doesn't fall into that range. So we only need to concentrate now on those 3. So we narrowed it down even more. For this equation to hold true, if this is been set as 1, then one of these has to be 1 and the other one has to be 0. So in my first scenario, I will say that n over k is my 1. Right? If this has been set as 1, this has to be 1 and 0. Or this has to be 0 and that has to be 1. So my first scenario is that I'm letting this n over k equal to 1. Now, the only way that's going to be equal to 1 is if you have the following parameters for n. N has got to be greater than k over 2, or has to be less than k. If it's in that range, then that will be 1. And then if this is 1, then this has to be 0 in order for it to match up. So we have to set 100 minus n over k equal to 0. And that will only happen for certain values of n. And we'll discuss that in a moment. Now let's look at the other scenario, which is when this is 0 and that is 1. So now n over k is 0 and this is 1. So that means in my second scenario, I'm setting n over k equal to 0. And that is true when n is less than k over 2, right? If n is less than half of k, n over k will be less than a half, and the closest integer to that is 0. Now we have to set this equal to 1. So that means 100 minus n over k, that is going to be equal to 1. So these are our two scenarios, and let's talk about these. First, let's talk about this one because it's a little bit easier. If 100 minus n over k is equal to 1, that is true when 100 minus n is greater than k over 2. But 100 is greater than k over 2 plus n. Because if you remember, this was my original range for n. And if that is my range for n, and you first look at this, the first thing, of course, you just put, let's say, the n on the other side. So you have k over 2 plus n, right? Now, n, according to this, is less than k. So if you continue this inequality, considering the fact that k is less than 99, then you can substitute k here. It's always going to be less than 100, right? Because it's less than or equal to 99. And then that is always going to be greater than k over 2, and it's also going to be greater than k over 2 plus n. And the reason this holds true is because of this condition that we had set earlier. And this is always true. So because it's always true, pk in this case is 1. Probability is 100. So 100%. So not much help there. So obviously the answer to our question is going to come from this part of the question. So now let's concentrate on that. We have a scenario that n is between k and k over 2, and we want this to equal 0. So that means we want 100 minus n to be less than k over 2. If it's less than k over 2, this will hold true. So rearranging this, that means 100 is less than k over 2 plus n. And let's take into consideration this inequality. So that means 100, which is less than k over 2 plus n, is also less than k over 2 plus k, right? Because n is less than k. And this, of course, is 3k over 2. Now what we have to do is remember our only remaining values of k were 67, 87, and 99. For each of these, let's figure out what we get. And we are using the inequality 100 is less minus this one right here. 100 minus k over 2, I'm just putting n in the middle, is less than 3k over 2. All right, so let's figure this out for k equals 67, 87, and 99. If k equals 67, we have the following numbers. 66.5 is less than n and less than 67. Because remember, n is less than k. Right here, our original parameter, n is less than k. So that I can't really go up to 3k plus 2. I can only really go up to k. So I can only write k there. So that's why when k is 67, we have these numbers. When k is 87, we will have 56.5 is less than n is less than 87. And then when k is 99, we will have n is less than 99 is greater than 50.5. And as you can clearly see, the range is smallest when k is 67, the range for n. So clearly the minimum pk is when k is 67. And if you're interested, the actual formula for calculating pk is 1 over 2 plus 1 over 2k. Interestingly, you don't even need to figure out what pk is. All you have to do is figure out which of those values of k in the denominator give the smallest range for n. But if you want, you can figure this out. And this is going to be 1/2 plus 1 over 2 times 67. And if you do the math, you'll get 34 over 67. But like I said, that 34 over 67 value is not even required. All you need to know to figure out this question is that k is 67 and that one of those denominators is 67. So regardless, we got the answer. And therefore, number 25, the answer is D. Let S xy, where x is an element of 0, 1, 2, 3, and 4, and y is an element of 0, 1, 2, 3, 4, 5, and xy does not equal 0, 0. Let T be the set of all right triangles whose vertices are in S. For every right triangle with T equal to triangle ABC, vertices ABC in counterclockwise order, the right angle at A. Let f at t equal tan of angle CBA. What is the product of all the f at t's? All right, so obviously we have to explain what they are talking about here. What they are saying is that you take this grid here, and the grid is labeled obviously 1 through 5 for the y and 1 through 4 for the x. So this is 0, 1, 2, 3, 4. And then for the y, this is 0, 1, 2, 3, 4, 5. Like that, right? And there's no origin. That's why if you notice there's a dot that's not filled in. There's no origin. That's what this means. The origin is not involved, so we'll get to that a little bit later. Then what you do is you create right triangles. So for example, here's one such right triangle, right? This would be a right triangle. And what you do is that for every such triangle that you create, let's create a bigger one. So I create a big one, let's say like this. For every such right triangle that you create, you label it A, B, C in counterclockwise order. Okay, counterclockwise order. All right, so A, B, and C. Okay, then that becomes obviously a triangle with vertices A, B, C. And then the right angle is at A. Okay, well, let me do that again. So A, B, C. All right, so I'm trying to understand this question. Okay, and then what you do is you take this f at t. f at t for that particular triangle is the tangent of the angle CBA. So CBA is this angle right here. So CBA, okay. So what is going to be the tangent? Well, tangent is, if I remember, over algebra, opposite over adjacent. So in this case, it's going to be CA or AC over the adjacent, which is AB. All right? So that is what they're saying. And then when you do that for every single possible triangle, you have to multiply them all. So it would be, well, if this is one result, you're going to get a whole bunch of results. You have to multiply them. That's what this means. So that's that symbol. Okay, so how do we approach this? All right. So let's talk about this. Let's discuss it first in simple terms. Well, obviously. Let's say I drew any such triangle like I just did, right? And I do basically the same story, ABC. And then, of course, the right angle is at A. And I'll label the sides X and Y. If I take the tan of CBA, angle CBA, it's going to basically be the tan of this angle. So it's X over Y. That is my F at T, according to this definition. But here's the part of the question that really helps if you can understand it. That for every such triangle, you can draw the exact flip of it. You can draw the same kind of triangle, but flipped. So instead of like that, it would be like this. Right? You can do that. You can do that for any triangle. And just maintain the order of the vertices. It's counterclockwise, right? So B is going to be here, and then C is going to be here. So AB this time is X, because I've just taken, it's like a mirror reflection, right? It's like a mirror reflection in that line I just drew, and this is Y. Now what is my F at T? Well, again, it's tan of CBA, CBA. This is my angle this time. So this time, tan of CBA is Y over X, correct? So if I were to start multiplying them together, right, this is my F at T for this triangle, and this is my F at T for this triangle. When I were to multiply those, what happens? Well, you get X over Y times Y over X, and that is equal to 1. So what that implies is that if you do this for every single triangle, and then each triangle has a matching pair, that's basically a flip of it, like the way I drew it, and then you did this F at T, and then multiply them all, it will all equal 1. And 1 is one of the answer choices. But it's not that simple for one reason, because we do not have an origin. If there was an origin there, then yeah, it would be 1. But we don't have an origin. And because there's no origin, we need to look at the triangles that actually go through the origin and exclude them. So let me write all that out. So to recap, notice we do not have an origin. Therefore, we need to look at all the triangles that pass through the origin and exclude them. And when you do, then we will be able to figure out what they want. And what they want, and I'll write it in layman's terms instead of making it messy and complicated. That big product, right? That big product that they want, if I do for all triangles, right? So all triangles, it would be equal to 1, right? And we had previously concluded that. But they don't want that answer. They want you to just figure out the triangles that go through everything except the origin. So everything except the origin. So I'm writing this out like this because I want you to understand it. So this is what they want you to figure out. Okay? But if you were to take this and multiply it by all the f at t's for the triangles that go through the origin, this is all of them, right? This is the triangles that go through everything except the origin. These are the triangles that go through the origin. So this is a complete set. And because it's a complete set, it equals all the triangles. This is what they want you to figure out. This we know already is 1. So all I have to do is figure out this. If I do, I plug it into here, and I can solve for this. All right? So I hope that makes sense. And this is completely and absolutely layman's terms notation. No mathematician would write it this way, but I want to explain it to you. So now I have to concentrate on this right here. I have to look at all the triangles that go through the origin and calculate f at t, and then multiply them. Okay, so here we go. That's where we need a diagram. There you go. There's a beautiful diagram of all the triangles that go through the origin. Here's the origin, and these are the bad guys. These are the ones that we have to put there. So it's fairly simple to figure out the f at t for each of these. Remember, f at t is equal to basically the tan of CBA. And for the first group here, it's a piece of cake to figure out the tan. So because these are all labeled, right? The lengths are easily countable. For example, this length is 1, and this length top to bottom is 5. So the tan of that, remember the right angle is at A, so this would be A, and this would be B, and this would be C, right? I'm just labeling this guy right here, that one. So the tan of CBA would basically be 1 over 5. Correct? So you do the same thing with all the other ones. It would be 2 over 5 for this next one. It'll be 3 over 5 and 4 over 5. So if we did the sum, remember that big sum that's up here, or actually not the sum, the product. It's been a long video. Sorry, I apologize. The product, I'm allowed to get tired too. The product is going to be 1 over 5 for this one. And then the next one would be 2 over 5. These are all tans, right? Tan of CBA. The next one is 3 over 5. And the fourth one is 4 over 5. So those tangents are fairly easy to figure out. Now for this one, these two triangles, it takes a little bit more of legwork, but it's not hard. You can just use Pythagoras to figure out, because if you want to figure out the side length of that one, this from here to here is what, 1, 2, 3, 4. From here to here is 1, 2, 3, 4. And you can just use Pythagoras, and I'll let you do that. That's pretty straightforward. But I'll just label it for you. For example, in this triangle, remember the right triangle is always at A, so that's going to be A. Counterclockwise, so counterclockwise is going this way, right? A, B, C. So tan of ABC, or tan of CBA, is going to be this over that, correct? So that's going to be, and like I said, I'll let you figure out the side lengths. There's only 2 triangles, and it's fairly simple. If you do, you'll get the following results. You'll get 4 root 2 over root 2 for one of them, and for the other one, you'll get side lengths of 3 root 2 over 2 root 2. And then when you multiply it all out, you'll get 144 over 625. All right? And that was in lowest terms. So now we go back here. And it's the final step. And I'll just write it over here. This equation was really just 1 plus our product of f at t that we want to figure out, everything except the origin. And then this guy, which we just figured out, was 144 over 625. And then to get this, all we have to do is just cross multiply. It would be 625 over 144. And that is the product that we are interested in. 625 over 144 for this question. And that means number 25, the answer is B. What is the sum of all positive real solutions to this equation? We are going to make a substitution that will help us, and that is x is equal to pi y over 2. And when you make that substitution, you get 2 cos pi y times the cos of pi y minus the cos of, it's going to be 4028 pi over y when you make that substitution. And on this side, it's going to be the cos of 2 pi y and minus 1. All right. So at this point, we have to use some angle identities. And those angle identities, I'm sure you know. In particular, it's the cos of 2x, and that is cos squared x minus sine squared x. Now, if you put it all in terms of sine, it becomes cos 2x is equal to 1 minus 2 sine squared x. And then if you put the sine squared on one side, it becomes 2 sine squared x is equal to 1 minus the cos of 2x. And there's variations. We can divide through by 2. Sine squared x is equal to 1/2 1 minus cos 2x. And so on, right? You can also multiply through by -1, and that will give you 1/2 times cos 2x minus 1. So as you can see, there's multiple variations. So we want to get it into a form that we have. And if I multiply this by 2 sine squared x, then I will get cos 2x minus 1. And that is the form that this is in. So all I did was just took some well-known identities and just made it into a form that we can use. So we can now use it to substitute there. It becomes minus 2 sine squared pi y. All right, using that angle identity. On this side, we can start multiplying this out. It's going to be 2 cos squared pi y and minus 2 cos pi y cos 4028 pi over y, like that. And we can now divide through by 2 and then put the cos squared and the y squared on one side. So we're going to have cos squared pi y plus sine squared pi y, and then put the other guy over on this side, like this, cos pi y times cos of 4028 pi over y. Well, as I'm sure you know, this is equal to 1. So that works out very nicely. Now, at this point, we have to start thinking about how we're going to proceed with this equation. Well, one solution is that cos pi y is equal to 1, and the cos of 4028 pi over y is also equal to 1. If both of these are 1, then this would work. And I think this is sufficient. So if you guys remember that cos graph, it's basically going back and forth like that, right? And we want to know, when is it 1? Well, it's 1 here at 0, it's 1 here. This is 1, right? At 360, so 2 pi. And then it's again going to be 1 here, which is 4 pi, like that. So basically what that tells me is that if this is true, if the cos of 4028 pi over y is 1, that means that 4028 pi over y has got to be equal to some multiple of 2 pi, as you can see from the graph. So 2 pi times k. Simplifying this, divide through by pi on both sides and divide through by 2, you get 2014 over y is equal to k. So now that basically means that y is some divisor of 2014. What are the divisors of 2014? Well, 2014 is 2 times 19 times 53. So y can be any divisor of 2014, so that's going to be 1, 2, 19, 53, 38, 106, 19 times 53, or 2 times 19 times 53, right? But the problem is that we have to ensure that this also matches. But the problem is that for 1, 19, 53, and 19 times 53, if you were to sub it into this guy here, it actually gives you a value of -1 if you were to do cos of pi y for those values of y. So those ones we can't include because we have to ensure that it gives me 1 for both. So the only ones I can use are 2, 38, 106, and 2 times 19 times 53. All right, so my y values are 2, 38, 106, and 2 times 19 times 53. So remember, my original substitution was x is equal to pi y over 2. So that means x will be pi, 19 pi, 53 pi, and 19 times 53 pi. So the sum of the values of x are basically pi plus 19 pi plus 53 pi plus 19 times 53 pi. And when you add all those up, you get 1080 pi. And therefore, the answer to number 25 is D. A bee starts flying from point P0. She flies 1 inch due east to point P1 for j greater than 1. Once the bee reaches point Pj, she turns 30 degrees counterclockwise and then flies j plus 1 inches straight to the point Pj plus 1. When the bee reaches P 2015, she is exactly a times root b plus c times root d inches away from P0, where a, b, c, and d are positive integers, and b and d are not divisible by the square of any prime. What is a plus b plus c plus d? Well, first let's draw a very basic drawing to get an understanding of what's happening. So first, we are going to start here. And this is going to be, of course, P0. And from there, we traveled 1 unit. And then we get to P1. And then from there, we have to kind of tilt 30 degrees. So this is basically 30 degrees in here. But this time, we have to actually go a little bit farther because we have to go 2 units this time. So we're traveling a little bit farther this time. So that is going to be 2. And then again, we have to now shift or tilt another 30 degrees. So if this is continuing, we have to go 30 degrees from that. So approximately something like this, like that. But we've got to go 3 this time in terms of our units. So this is P2 and this is P3 right here, and so on, right? You just keep on going like that. So I just wanted to give a very basic understanding of the question. Now you say, okay, well, how do I approach this? Our goal is to go from P0 all the way to P2015. In this diagram, I just showed you from P0 to P3, but we got to go all the way to 2015. And when we do that, eventually, what will happen is that we have traveled a certain distance in the x direction and a certain distance in the y direction. So in the end, we will take the distance in the x direction and the y direction and figure out the total distance using Pythagoras. So for example, if we had gone this much in the x direction and this much in the y direction, the total distance from P0 to P2015 will be calculated by a simple Pythagorean relationship. So we're going to first concentrate on this x distance, then on that y distance individually. So let's first talk a little bit about the x direction. When you're going from P0 to P1, well, that was very simple. It's just 1. And when you go from P1 to P2, okay, now we have to figure out what is my x direction. And that is where the angle comes into play. It's going to be 2 cos 30. That calculates my x direction from there to there. And just to be consistent, this was cos 0 actually. You don't really need to put that in, but it maintains some consistency with what I'm writing. Now, from P2 to P3, it's 3, but cos 60 this time, right? Because if you look at this angle is 60 degrees. And then in a very predictable way, from P3 to P4, it will be 4 cos another 30 degrees you tack on, and so on. So it just keeps on going like that. In a very similar way, if you look at the y direction, it would be 1 sine of 0, and then 2 sine of 30, and then 3 sine of 60, 4 sine 90, and so on, dot, dot, dot. And then we have to keep going all the way until we get to P2014 to P2015. But the good news is that there's a bit of a pattern here, and that's what I have to explain. So what I'm going to do is concentrate solely on the x direction, and then once we get the x direction, we can talk about the y direction. So the total sum, what I had written was 1 cos 0 plus 2 cos 30 plus 3 cos 60 plus 4 cos 90, and you get the idea, right? But then we have to start thinking about it, because we obviously are not going to write it all out. That would be, impossible. But we have to start thinking at what this is going to be. Eventually, when you get to 12, it's cos of 330, all right? And then 13 is cos of 360. But then, once you get to 360, you've gone one way around. So then it goes back to 0 again, cos of 0, right? 14 cos of 0, and so on, 15 cos 30, and you get the point. Dot, 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 and then I'll extrapolate all the way until the very end. Now, 2016 is not what we're going to get to, but the reason I wrote that is because every time it's a multiple of 12, it'll be cos 330. 2016 is an interesting number. Why? Because it is a multiple of 12. Exactly. So if it was in there, it would be 330 cos. But we're not going to that, so we don't need to include it. I just wanted to put it in there as a frame of reference. So one before it, which is what we definitely will include, will be the cos of 300. Okay, so that is how we get this whole thing. So I hope that makes sense. Now what we have to do is we have to adjust these angles. When you move right at theta degrees, it's the same as moving left at theta minus 180 degrees. So all of these can be adjusted as follows. We can keep the 1 cos 0, 2 cos 30, 3 cos 60, and all those guys, right? 4 cos 90, and so on. We can keep 5 cos 120, 6 cos 150. But once we get to 180, it's the same as 180 minus 180, which is 0, but in the opposite direction. So instead of 7 cos 180, it becomes negative 7 cos 0. So this is a very important point that allows us to simplify this. And then 8 cos 30 minus 8, and so on, dot, 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 until you get to 2015 cos 120. Now at this point, we have to carefully group like terms. So in front of all of the cos zeros, we have to put the proper numbers. And that is going to be 1 minus 7, and then plus 13, dot, dot, dot. And then eventually you will get plus 2005 minus 2011. And then we group what is next, which is cos of 30. And that's going to be 2 minus 8 plus 14. And then eventually you will get dot, 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 2 plus 2006 minus 2012. So let's continue in this fashion. Then we have the next one, which is going to be 3 minus 9 plus 15, dot, 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 and eventually you'll get to 2007 minus 2013, and that is cos 60. Then we get to the next one, 4 minus 10 plus 16 minus dot, 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 2008 minus 2014, and that is cos of 90. Then we get to 5 minus 11 plus 17, dot, 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 plus 2009 minus 2015, and that is cos 120. And I think there's one last one, plus 6 minus 12 plus 18 minus dot, 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 plus 2010 minus, I think that's it. We actually minus 2004, let's just put it 1 before, plus 2010. And then that says cos 150. All right, so we have grouped this very nicely. Now comes a little bit of a magic. Not really, but all of these, if you notice, are minus 6, dot, 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 minus 6, right? Cos 0. And then we're adding again minus 6, dot, 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 minus 6. And you get the point. You don't need me to walk you through every single one. So I'll just write them all out. Cos 30. So now that we've got these all grouped into minus 6's, we have to start adding them. Well, how many were there? If you go back and actually look at the terms, you'll see that if you do that count, it's 336 terms. So there's 336 terms that were here. Right there, 336. And this was also 336. This was also 336. From here to here, it was also 336. This was 336. And if you notice here, it actually didn't increase. It didn't go up to 2016. So this actually is only 335. And that's a very important point to assess. So I'll just write x. I'll just continue over here since it keeps it all on the same screen. So that means these guys, there's 336 divided by 2 of those negative 6's, because to get a negative 6 you had to combine 2. So since there was 336 terms, there's 336 divided by 2 of those minus 6's. So cos 0. And similarly, it'll be 336 divided by 2, which is 168, times minus 6, cos 30. And very similarly, 168 times minus 6, cos 60, plus 168 times minus 6, cos 90, plus 168 times minus 6, cos 120. Now the last one is the only one that is a bit tricky, because there's only 335, so that would mean there's 167 of those pairs, right? But then there's an additional one guy left over at the end without a pair, because there's no 2016 to subtract, so you just have to put that in there like that. Cos 150. All right, so significant progress is being made. Let's continue here. So we're going from here to here. And now we just have to multiply all these out. So it becomes minus 1008 cos 0 plus, or actually minus, they're all going to be minus 1008 cos 30, minus 1008 cos 60, minus 1008 cos 90, minus 1008 cos 120, and then this one is a little bit different, right? This one, when you do the math, it actually becomes plus 1008 cos 150. Okay, now all we have to do is factor out a minus 108 and then just now write out what is the values of all of these numbers. Well, the cos of 0 and so on. And this is going to be 1 plus root 3 over 2 plus 1/2 plus 0 minus 1/2 plus root 3 over 2. And when you add all these up, it just becomes 1008, and everything in the brackets there simplifies to, well, these two cancel, and then it just is 1 plus root 3. And there we go. All that hard work to get the final answer for x. But we also need to get y. Remember? Y direction all the way at the very end here. Well, the good news is that it pretty much is the exact same pattern. And yeah, I'll let you do that. I don't think you need me to talk you through it since it's identical. And when you do, at the very end, you'll get a very similar identical number, which is minus 1008 plus 1 plus root 3. All right, so now we have to use this formula right here. This d is equal to x squared plus y squared, right? So we had our x value as minus 1008, 1 plus root 3 after all that hard work. Y you get it by doing the exact same process, so I'll let you do that. And now we just have to figure out the distance with that formula. So plug that in, x squared plus y squared, and we get minus 1008, 1 plus root 3, all of this squared, plus y squared, which is again 1008 times 1 plus root 3, all squared. And this is all under the square root sign. So these are identical, so it just becomes really 2 times 1008 squared plus 1 plus times, I should say, 1 plus root 3 squared, all under the square root sign. So that becomes root 2 1008 1 plus root 3. If you multiply this out, you get 1008 times root 2 plus 1008 times root 6. And if you remember at the very end, or very beginning, I should say, that they told me that that distance is of the form a times root b plus c times root d, and they wanted you to figure out a plus b plus c plus d. Well, a in this case is 1008, b in this case is 2, c is 1008, and d in this case is 6. So that's 2016 plus 8, which is 2024. So that is the answer to a very challenging question, number 25. The answer is B. The sequence AN is defined recursively by A0 is 1. A1 is the 19th root of 2, or 2 to the 1 over 19. AN is AN minus 1 times AN minus 2 squared for n greater than or equal to 2. What is the smallest positive integer k such that the product A1, A2, dot, dot, dot until AK is an integer? Well, let's figure out a list and see what we get. A0, A1, and so on. Well, A0 they already gave me. A1 they say is 2 to the power of 1 over 19. And then A2 onwards, they've got this formula here, that AN is equal to AN minus 1 times AN minus 2 all squared. Okay, so A2 would be A1, which is 2 to the 1 over 19, times A0 squared. Well, that's just 2 to the 1 over 19. Okay, so put that here, 2 to the 1 over 19. A3 is going to be A2, which is 2 to the 1 over 19, times A1 squared, which is 2 to the 1 over 19 squared. And this is going to be 2 to the 1 over 19, and then you're not going to square the exponent, right? You just multiply it, so it becomes 2 over 19, like that. And then that, of course, you just add the exponents, so that becomes 2 to the power of 3 over 19. So I'll put that in here, 2 to the power of 3 over 19. Okay, let's keep going. Let's do a few more. A to the 4 is A to the 3, which is 2 to the power of 3 over 19, times A to the 2 squared, so 2 to the power of 1 over 19 squared. And that's going to be 2 to the power of 3 over 19 times 2 to the power of 2 over 19, and when you add the fraction, it becomes 5 over 19. A to the 4, 2 to the power of 5 over 19. Okay, don't really see a pattern yet, but maybe I don't even need a pattern. Let's just figure out, we've got time, right? We're doing this as practice, so, well, I'll do three more. A5, here we go. Well, A4, 2 to the 5 over 19 times A3 squared, 3 over 19, all squared. So that's going to be 2 to the 5 over 19 times 2 to the 6 over 19, and that becomes 2 to the 11 over 19. So this is 2 to the power of 11 over 19. A6, again, same story. 2 to the 11 over 19 times 2 to the 5 over 19 squared. And that is going to be 2 to the 21 over 19. Just save some steps there since you kind of get the idea by now. And we'll do one more. So this is going to be 2 to the 21 over 19, and then 2 to the 11 over 19 all squared. And when you do that math, you get 2 to the 43 over 19. All right, so it doesn't look like much of a pattern, but I did notice something by doing a lot of these, is that this exponent, whatever it is, it's always over 19. And it seems like you're taking this guy, well, right before it, and adding 2 times the one before it. So for example, let me explain what I mean by that. Let's say we had 2 to the power of a over 19 for a to k minus 1. And a to the k minus 2 is 2 to the power of b over 19. When you do a to the power of k, it looks like it's going to be a plus 2b. And you can test that out. For example, this guy was 21 plus 2 times 11, which is 22. And this one was 11 plus 2 times 5, which is 10. And 10 plus 11 was 21. So this is really sort of our formula, where the one before it, ak minus 1, is a over 19, and ak minus 2 is b over 19. All right, so based on that, let's create more of an extrapolation. Now the answer choices go up to 17, all the way from 17 to 21, so they're making us work a little bit, but that's okay. We've got time, we can do this. Our big product, A1, A2, A3, dot, 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 all the way till AK, is basically adding the exponents. It's a sum. So it'd be 2 to the power of 1 over 19, and then you're going to add up all the sums. So if you remember, this was 1, and then 3, and then 5, 11. You're just going to add them, right? Because when you're multiplying these numbers, you're going to be adding the exponents. Simple exponent law. So it's 1 plus 1 plus 3 plus 5 plus 11 plus 21 plus 43. These are the ones we've already figured out. But I'm going to figure out, obviously, a few more. And this is going to be the next one, 85. And the way I can do it really quickly is this. You just take the previous one and add to it 2 times that. So in this case, it would be 43 plus 42, which is 85. So it's not really that complicated. 171, 341, 683, 1365. Numbers are getting larger, but I think the math is reasonable. 2731 plus 5461 plus 10925 plus 23, that is, and plus 21846. Now at this point, I'm going to stop. Why? Well, because I've got up to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This was when k is 16. Now I've got to see what happens when k is 17, because that was the first of my answer choices. So far, we're just figuring out a chain of numbers. Okay, when it's 17, then that's when we actually need to know what happens. So when it's 17, the number is as follows: 4361, 43691. Okay, let's see. 2 to the power of 1 over 19. So this would be A1, A2, all the way till A17. Now we got to add up all these guys. This, and this. And when you do, you get the following number, 87381. Now, what is 8731 divided by 19? It is 4599. It is an integer. So perfect. And that means we've done it. They've asked, what is the smallest possible integer case such that that product is an integer? We got the answer. We got it for k is equal to 17. And it's nice of them to have made the very first answer choice the correct one, because otherwise we'd have to go on to 18 and 19 and 20 and 21. I think they took some mercy on us. So number 25, excellent question. The answer is A. Circles W1, W2, and W3 each have radius 4 and are placed in the plane so that each circle is externally tangent to the other two. Points P1, P2, and P3 lie on W1, W2, and W3 respectively, so that P1, P2 equals P2, P3 equals P3, P1. And the line PI, PI plus 1 is tangent to WI for each I equal to 1, 2, and 3, where P4 is equal to P1. See figure below. The area of triangle P1, P2, P3 can be written in the form root A plus root B, where A and B are positive integers. What is A plus B? So the first thing I'm going to do is draw some helpful lines. The first line is going to be from the center to P. So like this. And I can label that center. Let's just label it approximately here. And I'm going to call that O1. And the second one, very similarly, if this is, say, O2, that center, I will draw a line from P2 through that. So it will be approximately like this. And then the intersection point of those two green lines, I will call K. So K is right there. Okay, so now they had told me that this line right here is tangent to the circle. So that means that this angle is 90 degrees. And if that angle is 90 degrees, then this angle is 90 degrees. And this triangle is equilateral. That's pretty much what that means. All the sides are the same. So that means this angle is 60 degrees. And in a very similar way, this is also the tangent, and therefore this is 90 degrees. And if that's the case, if this is 90 degrees, then this will be 30. 90 minus that 60. So put 30 in there. And therefore this angle must be 60. So we've got ourselves a 30, 60, 90 triangle. And as always, the ratio of the sides are 2, 1, and root 3. So I will call this D. This will be 2D. And this from here to here is root 3D. Those distances. So now we will draw one final line from O1 connecting it to O2. And at this point we can proceed with law of cosines. And law of cosines in particular on the triangle that has been created from the points O1, K, and O2. So that triangle, we will use law of cosines. So O1 to O2, I'll just write out the lengths instead of making the diagram messy. That is the distance from the center of one circle to another. So the distance is basically 2 radii. And since the radii is 4, that distance is 8. The next side of that triangle O1 to K, well, from here to here is the radius, which is 4, and from here to here is D, so it's 4 plus D. And then the other side, which is right here, that is O2K, this whole distance from there to there is 2D, and this distance is 4, so it would be 2D minus 4. So now let's proceed with the law of cosines. 8 squared is equal to 4 plus D squared plus 2D minus 4 squared minus 2 times D plus 4 times 2D minus 4 cos of, what's the angle? The angle is 60. So now let's do this. We have a little bit of room here. 64 is equal to D squared plus 8D plus 16 plus 4d squared minus 16d plus 16. Now the cos of 60 is a half, so that will just cancel with that 2. So I can just expand those two guys now. 2d squared minus 4d plus 8d minus 16. Okay, so now we just have to collect like terms and all that stuff. So 64 is equal to d squared, 5d squared actually. This guy and this guy. And then minus 8d plus 32 minus 2d squared. And then that's 8 minus 4, 4. So minus 4d and then plus 16. And then putting it all together, it's going to be 3d squared. And then let's see here, minus 12d. And it will be minus 16. And that equals 0. Okay, great. So now all I have to do is just figure out d using Pythagoras. Using the quadratic formula. So 12 plus or minus the square root of minus 12 squared minus 4ac all over 2 times 3. So this is 12 plus or minus 144 minus 144 plus 192 all over 6. And that looks like 2 plus or minus 144 plus 192 is 336. And 336, I believe that is 4 root 21 all over 6. So there we go. Or you can simplify this a little bit further. First and foremost, we need the positive value because d represents, of course, a distance. And then this can just be root 21 over 3. 2 root 21 over 3. So d is that. So we can now figure out the side length of that equilateral triangle, which is root 3 times d. So root 3 times d would be 2 root 3 plus 2 times root 63 over 3, which is 2 root 3 plus, what's that, 9 times 7, so it'd be 2 times 3, so 6 divided by 3 is 2, so 2 root 7. Okay, and that is the side length of the equilateral triangle. Now, I hope you remember the area of an equilateral triangle. There's a formula for that. It is very beneficial to know that because it saves a lot of time. And that is that the area would be root 3 over 4 times a squared, where a is the side length. And this is our a. So use that formula. A would be root 3 over 4 times 2 root 3 plus 2 root 7 all squared. And let's expand this now. So root 3 over 4, it would be 2 root 3 times 2 root 3, so it would be 3 times 4, which is 12. And then you would have 2 times 2, 4, and then 8 root 21 plus 2 times 2, 4 times 7, 28. So this is root 3 over 4 plus 40 plus 8 root 21. So this is going to be 10 root 3. And then this will be 8 root 63. So it'll be 10 root 3, and 63, as before, was 3 times 7. So it'd be 3 times 8, which is 24 over 4, which is 6. So 6 root 7. Okay, but they're saying that it's got to be in this form. Just root A and just root B. So we have a mixed root where they don't want that. So that's okay. I can just put it inside. So it would be 3 times 100. So root 300. And this one would be 36 times 7, which is 252. And this is the form that they want. Root A plus root B. and then they want you to figure out A plus B. Well, A is 300, B is 252, and therefore 300 plus 252 is 552. 552 is the answer, and therefore number 25, that would mean D. Let ABCD be a convex quadrilateral with BC equal to 2 and CD equal to 6. Suppose that the centroids of ABC, BCD, and ACD form the vertices of an equilateral triangle. What is the maximum possible value of ABCD? Here is a diagram that illustrates what has been represented in the question stem. Now let's look at a few things here. The first thing I'd like to look at is the fact that AG1, that is 2 times G1M. So what does that mean? Well, this is the centroid, right? And the centroid has a property that it always cuts the line that is joining into a 2-to-1 ratio. So that's why I have this formula, that A to G1 is 2 times G1 to M. And very similarly, DG2 is going to be 2G2M. And of course, very similarly, the other one, which would be not represented here just to avoid making the diagram more messy, it would be the same for the other centroid, which is G3. Same kind of story, that it's a 2-to-1 ratio. Now looking at these two, we immediately will be able to recognize that two triangles, MAD, which is M to A to D like that, is similar to triangle MG1, G2. MG1 to G2 right there. And because of that, we can conclude that AD is equal to 3G1 times G2. And the reason is because since this is going to be 1/3 of AM, then this will be 1/3 of that, because the triangles are similar. And we can also conclude from that AD, that line, is parallel to G1, G2. In a very similar way, since G1, G2, and G3 form an equilateral triangle, then each of these sides are the same. And we can give that, I don't know, whatever you want to call it, we can call it S, let's say. So that means G1 to G2, which is also S, this is 3S. Okay, so AD is equal to 3S. Now let's look at AB. In a very similar way, because these triangles are similar, A to B is the same as 3G2, G3. And we can make that conclusion because G2 to M is 1/3 of D to M, and therefore if we're looking at other sides, we can conclude that G2, G3 is going to be 1/3 of A to B. So again, G2, G3 is S, so AB is equal to 3S. And we can also conclude that AB is perpendicular to G1 and G3, like that. And in the same way, we can do this exact same thing for the third side, which is BD. BD will be equal to 3G1, G3, which is equal to 3S. So BD is equal to AB is equal to AD, and that concludes that triangle ABD is equilateral. So a lot of hard work just to show this, but that is a requirement in order to proceed with the question. So here we go, next part of the question. If they had told us that in the question stem, it would have saved us a lot of time, but it's number 25 and they want to make it difficult for us. Okay, let's continue with this question. Now let's look at triangle BCD. B, C, and D, that we can figure out the area, at least part of it, using a formula that a lot of you know, 1/2 base times height. But in this case, it's not a right angle. So because it's not a right angle, we have to multiply it by the sine of theta, which in this case is this angle right here. That angle right there. I'll just put it in a format like that, and I'll just write it out here that theta is angle BCD. Okay, the question stem told me the values of BC and CD, 2 and 6. So this just becomes 6 sine theta. All right. Now we will use the law of cosines on this triangle BCD. Same triangle. And when we do, we get the following. BD squared is equal to BC squared plus CD squared minus 2BC CD cos theta again. So BD squared, BC is 4, well, it's 2, but if you square it, it's 4. Then that would be 36 minus 2 times 6 cos theta. And that looks like 40 minus 24 cos theta. That's for BD squared. Now at this point, we can use the fact that ABD is equilateral. ABD is equilateral. And what we are going to do is break up ABCD into 2 sections. The first section is going to be this ABD, triangle ABD. And then the second section, of course, will be the other part of that, which would be BCD, triangle BCD. Now the first part, which is ABD, this guy, that we had gone through painstakingly to prove is equilateral. And that helps us because it helps us figure out the area. So the area of ABD, if you know the formula for the area of an equilateral triangle, it helps save time, is root 3 over 4 times s squared, where s is the length of the side. And one of the sides of ABD is BD, right here. And BD, we know, is right here. Actually, we even know BD squared. So this s squared is this right here. So in a very nice way, it all kind of fits and works out. 40 minus 24 cos theta. And when you simplify that a little bit, we get 10 root 3 minus 6 root 3 cos theta. Okay, so that takes care of this, at least for now. We still have to eventually handle the theta in some way, but at least we've got an expression for that. Now let's try to get an expression for BCD. Okay, well BCD I think we already did right here, 6 sine theta. So we've got it. We've got everything. ABCD is equal to ABD, that triangle, plus the triangle BCD. And we have ABD as 10 root 3 minus 6 root 3 cos theta. And BCD we have up here as 6 sine theta. Well, it would be great if I knew the numerical value for theta, but unfortunately I don't. So somehow I've got to figure out what this is equal to. And what I'm really trying to figure out is the max value of this. So let's see what I get when I kind of play around with these numbers here. And this is where it's not necessarily a trick. It's just more of an identification of a trig identity. And the first thing I'm going to do is sort of make it into a trig identity. So if I factor out a 12, something very cool happens. This becomes 1/2 sine theta, and then this part would become minus root 3 over 2 cos theta. And this is a trig identity. And some of you may know it, some of you may not. It is sine of theta minus 60. That is what it would boil down to. Because if you remember, if you expanded that trig identity, it's, and we get that really from this trig identity right here. So this is this, entirely based on that identity. So now we are in a very good position to figure out the max. Sine of something. Well, the maximum value of the sine of anything is 1. So the maximum value of that is 1. And therefore the max of the whole thing would be 10 root 3 plus 12 times 1, which is just 10 root 3 plus 12. This is the answer. And that happens when this angle is 90. So when theta minus 60 is equal to 90, and therefore theta is actually 150, just in case you wanted to know. 10 root 3 plus 12 is the answer to this very challenging question, and that would be C for number 25. For each real number a with a between 0 and 1 inclusive, let numbers x and y be chosen independently at random from the intervals 0a and 0,1 respectively, and let p at a be the probability that sine of pi x squared plus sine of pi y squared is greater than 1. What is the maximum value of pa? So we have sine of pi x all squared plus the sine of pi y all squared. And that is greater than 1. So what I'm going to do is look at the boundary first, and then we'll talk about the greater than. So the boundary would be the 1. Now, we know from our trig identity that 1 can be written as sine squared anything plus cos squared anything. So I will write it as sine squared pi x plus cos squared pi x. That's one of the more commonly remembered trig identities of the many, many identities. So that means this cancels with that, and all you're left with is sine squared pi y is equal to cos squared pi x. We still don't have the same variable. Now we get into one of the lesser known trig identities, and that is as follows. This can be written as follows. It can be written as sine squared pi 1/2 plus or minus x. So that is one of the more lesser known. So for example, that is going to be equal to sine squared pi y. So for example, if x was 1, then cos squared pi would be equal to negative 1 squared, which is 1. So that would mean cos squared pi times 1, and that's going to be just 1. And then you plugged it into here, it would become, well, for either one, it would give you, say, if x is 1, it would be, if you use the positive, it would be 3 over 2 times pi, which is 270. Sine of 270 is negative 1, and when you square it, it becomes, again, 1. So that's when we have 3 over 2. And then if you use the negative, this guy right here, it would be 1/2 minus 1, which is negative 1/2. And negative 1/2 of 180 degrees is negative 90. And the sine of that is also negative 1. When you square it, it's a 1. So I just wanted to show you that this identity definitely does work. And I think that's one of the harder identities to remember. But nevertheless, here we go. Well, now that we have that, we can equate. That means pi y is equal to pi 1/2 plus or minus x. And this gives me two equations. It gives me pi y is equal to pi 1/2 plus x. And it gives me pi y is equal to pi 1/2 minus x. So drop the pi's, and this gives you 1/2 plus x. That's a nice equation. Drop the pi's here, and we get 1/2 minus x. Again, a very nice equation to work with. But we have more solutions, because if you took the square root of both sides, you would have a situation where you'd have sines taking the square root of both sides. We'd have sine of pi y is equal to minus sine of pi. I initially just did the plus, right? But now we also have to do the minus, because that's going to give me another. Well, again, we use another one of those trig identities that if you have this out front, like here, you can put it inside. So it would be the sine of minus pi, and then the rest is the same, like that. Okay, so now this will give me a couple more, I think. I have this line and this line so far. This, if I equate that, it's going to be pi y is equal to minus pi 1/2 plus x. And then the other one would be pi y is equal to minus pi 1/2 minus x. Drop the pi's and I get y is equal to minus 1/2 minus x. Drop the pi's here and I get y is equal to minus 1/2 plus x. Okay, great. Now I take those four equations that are just lines, and I will plot them. Initially, I'll plot them exactly the way they are, and then I have to translate them, and I'll explain all that. So plotting these are easy. When x is 0, we have a half, and then when x is negative a half, you have 0, and so on, right? So you can easily plot those 4 lines, and when you do, and you combine them, you get a shape that looks like this. Now, I have to now shift the graph to match our boundaries. I have to shift to the unit square. Now you say, well, what are you talking about, unit square? Well, let me draw the unit square first, and then I'll talk about it. So here is my unit square. Now, where did this unit square come from? Well, it came directly from the question. You see, the intervals of x are chosen from 0 to a, but a is between 0 and 1, and then y is chosen from 0 to 1. So that is where the unit square comes from. So for example, I'll write it out here. X is chosen from the interval 0 to a. And y is chosen from the interval 0 to 1. So this is x, and this is y. Well, y is from 0 to 1, so this is 0 to 1. So y is definitely all the way from there to there. There's no discrepancy there. But x is from 0 to a. But a, they're telling me, is anywhere between 1 to 0. I don't know what the value of a is. It's somewhere between 0 and 1. So a could be here, a could be here, I don't know. So let's just leave that alone. But one thing we do know is that the maximum that a could be is 1, and the minimum is 0. So the range for a is between 0 and 1. Now what we have to do is we have to translate that. We have to shift that to match here, because our boundaries are 0 to 1 on the x-axis and 0 to 1 on the y-axis. So we have to shift the graph to match our boundaries. Okay, and that's not a problem. I can just draw that same shape here, and hopefully it'll be somewhat accurate like that. Okay, there we go. Now we have to start talking about that P at A, that whole thing that they were discussing. P at A is the probability that that equation happens, the probability that this is greater than 1. Now it will be greater than 1 if it has values inside the shape. So if you don't believe me, we can look at this. It's sine squared pi x plus cos squared pi y, and we want it to be greater than 1. Well, it's got to be inside that shape. Let's test it out, because either it's inside or outside, right? So let's just test out some point inside this. I'll just say that is xy is a quarter and then y is 0. And let's see what happens to this equation. When we have x equal to a quarter, it's going to be the sine squared of 180 divided by 445, and then 0, so cos squared is 0. Well, sine of 45 is 1 over root 2, so if you square it, you get a half. And the cos of 0, well, you know that is 1. So when you square that, it's 1. And 1 plus a half is 3 over 2, and of course that is indeed greater than 1. So that means points got to be inside. So that's just something I wanted to show to illustrate that we now are working with this unit square, and in particular points that are inside. So now we have to talk about the probability that P at A. We have to maximize this P at A. Well, what is P at A? It's the probability that something lies inside this shape that is surrounded by green, so some point in there, divided by the total region for some value of A. Okay, so let me illustrate. Let's say my A is here, and I don't know what the value of A is, but I've just put it there. And then therefore, what is my region? Well, my region therefore was just going to be until that point. So my region, if that is where A is, my total region is this total area. And like any probability question, the total goes in the denominator. So what's the area of that total? Well, from here to here is A, from here to here is 1, so it's a rectangle with the dimensions A times 1. Now the numerator is our specific condition, and that is that it's got to be within that boundary. So I've got to figure out the area of that in terms of A. Now, there's two scenarios. The first scenario is that the way I drew it right now, that A is greater than a half. So if this is a half, it's on that right side of the half. The other scenario is if A is less than a half, less than or equal to a half. And that's, of course, when A would be here, let's say. So I've got to figure out the probability for both and compare them and then proceed with the maximum. Okay, so it doesn't really matter. Let's do the A less than a half first. So if A is less than a half, it's something like this, right? Where this is my value of A. Okay, so let's figure that out. P at A, therefore, would be as follows. It would be the area of the total, which I have already illustrated was A plus 1. That's just a rectangle. And then the area this time of that triangle. So that triangle, if we draw that line, that's like, representing an altitude. 1/2 base times height. The base is from here to here, and the height is from here to here. Well, the height is easy. That's just A. And the base, well, here's the thing. This is an altitude. So that's 90. And then the shape was giving me 45-degree angles. If you looked at those original lines, the slopes were all 1. So those are 45-degree angles. So that means this is 45 degrees, and this is 45 degrees. So that means that this is an isosceles triangle. So from here to here is the same as from there to there. Since that is A, this is A, and therefore that's A. So the base is 2A. So that just gives me A squared over A. And that's just A. And A is less than a half. So less than a half. So when A is less than a half, the probability is less than a half. All right? We want to maximize the probability. So let's see what happens when A is greater than a half. When A is greater than a half, now I've got to do pretty much the same thing. But this time, I have to look at a slightly different set of shapes. The total probability, again, is that rectangle. That's not going to change, so that's just A times 1. But now the numerator, that is a little bit different. That numerator now is this guy right here. You see that? And I'm going to break that up into 2. So I've got the triangle, this guy. And then I've got a trapezoid right here. So keep that in mind. So triangle, I'll just write that here, triangle plus trapezoid. So we are going to need some space, so I'll write that over here. And that's going to be all over A. Okay, so now let's carefully figure out this area. Triangle and trapezoid. Okay, triangle should be easy. That's 1/2 base times height. So 1/2 base, well, the base is all the way top to bottom. That's just 1. The height is from here to here. That's just 1/2. So as I said, the triangle part is easy. Trapezoid is a little bit more complicated. First of all, do you know how to figure out the area of a trapezoid? Here's the trapezoid. If this is A, this is B, this is the height. The area of a trapezoid is A plus B divided by 2 times the height. So this trapezoid, this is my first length, that's just 1. This is my second length. Okay, I got to figure out that second length. So I've got to do a little bit of brainstorming here. Let's figure this out now. All right, so what is this distance from there to there? Be careful. It's not A, it's A minus 1/2. This distance. So A minus 1/2. Now, previously I had gone through the angles. This is 45 and this is 45. So that means this is the same as that. So this distance is also A minus 1/2. And you can do the same sort of story up there to show that that is A minus 1/2. So this distance would be the full top to bottom, which is 1, minus 2 of those, A minus 1/2. So that's just going to be 1 minus 2A plus 1. So that's 2 minus 2A. All right. So plus 2 minus 2A all over 2, and then multiply by the height. The height is from here to here, and that is A minus 1/2. All right, this is the equation we have to simplify and maximize. So here we go. So this is going to be 1/4, and then when we multiply this out, we're going to have plus, it looks like 3 minus 2A over 2. And then this will be A minus 1/2. And then the A, I can immediately just invert and multiply to make this 4A and 2A. Might as well just put it in there. So now this will be 1 over 4A, and then multiply this out. I'm going to put the 1 over 2A out here and just multiply what's remaining. So that's going to be 3A minus 3 over 2 minus 2A squared plus, it looks like A. Okay, so we've got 1 over 4A, and then now let's use the multiplication of the fraction. So that's going to give me just 3 over 2 minus 3 over 4A, and then this looks like just minus A, and that's just plus 1/2. All right, great. So adding all the like terms, it looks like a minus A plus 2 minus 2 over 4A, and that is minus A plus 2 minus 1 over 2A. All right, great. So that means that's 2 minus A plus 1 over 2A. And this is our P at A, and this is something we need to maximize. Well, at this point, it's going to be maximized when this is the minimum, right? The smaller this is, the bigger this whole thing will be. So now I'm going to concentrate on minimizing that part. So to minimize that, I've got two sums. So this is where I have to use AMGM, arithmetic mean, geometric mean. And some of you may remember, an arithmetic mean of two numbers is A plus B divided by 2, the average. Geometric mean of two numbers is given by A times B, square root. And the arithmetic mean, AM, is always greater than or equal to the geometric mean. And if I multiply through by 2, you can write it as A plus B is equal to 2 times AB. So this is used on math contests, not very commonly, but can be used. So now compare this to this. This is also a sum of two things. So that means A plus 1 over 2A would be greater than or equal to. This is my A, so, well, that's just A. This is my B now, so I'll put that here, 1 over 2A. So A plus 1 over 2A is greater than or equal to, well, the A's cancel and you just get 1 over root 2. And therefore, that is going to be, that's just root 2, right? 2 divided by root 2 is root 2. So that means that A plus 1 over 2A is greater than or equal to root 2. So the smallest possible value is root 2. So the minimum possible value of that is root 2, so that's what I'm going to put in. And that gives me my maximum possible value of P at A. And before I circle that as an answer, I have to do one final step, is that compare it to this, because remember that was the probability I got when A was less than a half. And when I compare less than a half to 2 minus root 2, this is of course the maximum of those two. So 2 minus root 2 is the answer to this very challenging question, number 25, and that would be choice B. Let S be the set of lattice points in the coordinate plane, both of whose coordinates are integers between 1 and 30, inclusive. Exactly 300 points in S lie on or below a line with the equation y equals mx. The possible values of m lie in an interval of length a over b, where a and b are relatively prime positive integers. What is a plus b? On the AMC exams, graph paper is allowed, and so are rulers. So you will take your ruler and graph paper and try to figure out this question. And it's very time consuming, actually. I'm always amazed at how time consuming these questions are, because you have 3 minutes to solve it. So here we go. And here we go. It's a masterpiece, right? So let's explain this. We have all the plots here, all the lattice points, basically. And we have to see if we have exactly 300 points below the line y equals mx. Now, y equals mx, the solid line, we'll talk about the dashed line a little bit later, but let's just look at the solid line. The solid line is the equation y equals mx plus b. Now, since y equals mx plus b, when we draw it, we want 300 points, exactly 300, not 301, not 299, exactly 300. The total number of points, since it's a 30 by 30 grid, the total number of points will be 900. And we want 300, so basically we want a third of them below that line. So that means that most likely this is going to be a situation where m is rise over run. The run is easy, that's just 30. And the rise is going to be from there to there. And if you count those dots, it's 20. So the slope looks like m over 3. So that is what you call the lower bound. And then later we'll figure out the upper bound, but at least this is the lower bound. Now, we have to actually be convinced that this is indeed 300 points. We can't just guess. And the good news is you can do it pretty quickly. You can count the number of dots. So for here, it's 0. The number of dots here is 1, then 2, then 2, then 3, then 4, and then 4, and then 5, and so on. So I'll write them all out. And there you go. And we can add this up pretty quickly. It looks like every 3 we've got a situation where we have one number and then 2 of the next number. So we can easily just say 1 plus 2 plus 3 all the way until 20, because that would take care of these guys here. And then once those are taken care of, we're left with 2, 4, 6, 8, 10, 12, 14, 16, and 18. And we can add those up pretty quickly. So the sum from 1 to 20, well, that's just 20 times 21 divided by 2, and that's 210. And then these ones, you can easily manually add them up, and when you do, that's 90. So 210 plus 90 is indeed 300. So indeed, when we drew the line with m equal to 2/3, we got exactly 300 points below that line. Okay, so we're convinced that the lower bound is correct. Great. Now we need the upper bound. The upper bound is such so that the number still remains 300. So we got the lower bound, but then the upper bound is going to be open, meaning it won't touch it. It'll come close to it, but it won't touch it, because if it touches it, then we're going to end up adding another lattice points, and this will become 301. And we can't do that. We can't have 301. It has to be exactly 300. And that dashed line, I hope you can see it. It's right here. It represents the upper bound. And that upper bound, as you can see, touches this point. And if we included it, it would become one extra lattice point, 301, but we're not going to include it. That's why we're putting a curve here to show that it goes to that point, but it does not include it. Well, since it touches that point, we can easily use that to figure out the slope. The slope is just rise over run, right? Rise over run. And the rise looks like, well, we have to count it. Well, I already did. It's right there, 18. And the run is 28. So that slope, the rise is 18 and the run is 28. But here's the thing. This 18 was only until here. I have to include one more because that upper bound approaches that lattice point. So instead of 18 over 28, it's 19 over 28. And therefore that goes there. Now I know the confusing part is you say, well, if we are including that, then we're including one extra lattice point. So this 300 will become 301, right? How is that valid? Well, because we're not including that point. We're approaching it. And that's what that curve means, that we are not including. We're getting as close as possible to 19 over 28 for the value of m, but not including. All right, so that's about as best as I can explain it. So now we have to figure out the range. And the range is between 19 over 28 and 2/3. So we got to do this math here. And that looks like, if you do that, it's 1 over 84. And that is basically the interval. And it's in the form a over b, right? So this is my interval, range, whatever you want to call it. So a plus b would be just 1 plus 84. And that is 85. For this very challenging and time-consuming question 25, the answer is E.